Okay, so welcome everyone to the second session of the day. We were talking about measuring before, so how we work with data to, I guess, create measures of the economy that capture its complexity and its evolution more effectively. Now we're going to get into a conversation about modeling, which is okay. We have all of this data. We have the traditional data. We have new types of data, new types of indicators. How can we use it to answer important research questions? And we're going to begin with Clancy from Institute for Progress, who's going to be talking about recombinant innovation. Okay. 10 minutes and 5 minutes for questions, and I'm going to give 15 and 5 minutes.
Okay. Everybody, thanks for having me here. I work for the Institute of Progress, where I write a living literature review on the economics of innovation and social science research related to innovation. And so I'm going to this is going to be a talk kind of rounding up evidence about this question about, is innovation a process of combination, which I think is one way of modeling innovation. It's not the only way, but I think it's a very sort of long-standing way. There's classic quotes people throw up to sort of motivate. Is innovation a process of combination? Abbott, Pace, and Usher, the famous Einstein. But we want to try and go beyond sort of this evidence that's based on sort of famous people's quotes. Also, there's a sense in which these observations are sort of like they could be banal and not actually interesting, because like everything is a combination defined in some way. You know, it just means you can subdivide it into parts. Stuff is made of atoms. So yeah, everything's a combination, but maybe that's not interesting. And I think we have, fortunately, some good evidence that this idea that innovation is about combination, that's true in an interesting way. So what I'm going to do today is just talk about a couple different papers that document this underlying fact that new and unusual combinations are sort of interesting. They're important in science and technology. And then at the end, I'll talk a little bit about some implications that might follow from that observation. And I think what's useful about looking at a lot of different papers is each paper can kind of prove it in one way, but they always have holes. But if you look at a suite of different approaches using different measures, hopefully we start to be convinced at the end. This isn't physics where we can just do one perfect experiment and prove the day. I think in social science, we need lots of approaches that go together. So the question we have to answer is, how are we going to measure inventions and ideas, elements that are being combined? What does newness mean? And what do we mean by important? So when we talk about inventions and ideas, I'm going to look at papers that talk about patents and papers. Each of these is, of course, imperfect. Patents are not a perfect reflection of the innovation landscape, as everybody knows, but they have a lot of good information you can use about what gets combined. Similarly with papers, I think they're a little bit more reflective on the scientific work that goes on, but we'll look at both. What's combined? Well, with patents, we're going to use the patent classification system in most of these papers. And also a lot of papers look at the citations patents make and the class that those citations belong to. And when we talk about papers, the papers I'm going to talk about today tend to rely on two approaches. The most common is the one on the right, where you look at the list of citations made by a paper and you look at the journals that get cited. And you know, this paper we're going to actually talk about, but it cited Research Policy, it cited Strategic Management Journal. That gives us an indication of the kinds of ideas that this paper draws on. What I think is really interesting is look how coarse this stuff is compared to sort of some of the stuff we've been talking about in the earlier section on modeling. And so I think down the road, it'll be really interesting to see if new measures of sort of new, more sophisticated ways to develop these taxonomies can give us like much finer and nicer combinatorial measures. But anyway, the other one is keywords submitted by the authors. And how do we measure these other factors? I'll just go into the papers because they all sort of take different approaches. But when we talk about importance, I'm going to look at 4 different measures. How often do things get cited? These new indices of how disruptive a paper is. I'm sneaking in a little bit of my own work on Inventio. This got like converted from PowerPoint to Google Slides, and so there'll probably be little bugs throughout. And then there's some new papers, or at least one new paper, trying to look at even productivity. And so any one of these, maybe we can say, there's some problems. But when we get all four together, I think we get to be more confident. So this is probably the most classic line. There's a ton of literature in here about, looking at patents, looking at different ways to assess how they combine classifications, and showing that making weird combinations, you tend to get more citations. Okay, so this first one, He and Luo, all the different classes assigned to a patent, you can make a pairwise combination for each one of those, and you can line them up from the most unusual combinations based on historical patterns to the most common, and they sort of look at the 10th percentile of the unusual side of the combinations, and the weirder your combinations, the more probability, or the higher the probability you'll be a top-cited patent. Similarly, an old paper by Fleming, for him, newness is just how many times have people used this exact particular combination. Arts and Boigler's, they're looking at, does your patent make at least one connection that nobody else has made between different classes? Different ways of defining newness, different sets of patents sometimes, different levels of aggregation for the elements being combined, but they all point in the same direction. If you're doing weird new stuff, you're more likely to get cited. Similarly with patents, we've got two different measures here. On the left, that journal measure where you're looking at weird combinations of journals. And on the right, the keywords submitted by authors. Again, these are both showing what's the probability that you're in the top, say, 1% most highly cited paper for your field and your year. The weirder combinations tend to be more highly cited. There's a lot of extra complexity besides just, how the road to getting these citations, but I'm kind of skipping all that right for this presentation. So anyway, this is citations, and I think it's a start, and it's nice because we've got data on individual inventions, but also it's not the actual thing we maybe care about if we care about impact. Another line of work that's really new has looked at these disruptiveness indexes. So the way these papers measure disruption is they say, let's look at the citations you do receive, and we'll see if the people who cite you also cite your citations, or do they just cite you? If they just cite you, it's kind of like saying you made the old stuff obsolete, and now everybody's only looking at you, and they're no longer building on the earlier work. But if they cite you and everybody who came before you, you're kind of in the tradition, continuing on. And this paper by Lin, Evans, and Wu, they look at, again, weird combinations of journals. So my example on the left, if I'm citing a bunch of economics journals, that's not that unusual. And I'm less likely to be one of these disruptive papers. The people who cite me also cite my papers. And on the right, I'm citing an economics journal and a quantum physics journal. That's really weird. And I have a higher probability of being one of these disruptive guys. So again, I think this is interesting and starts to be suggestive of what I think is really going on here, which is that when you make a new combination, you create a new platform for collaboration and lots of new subsequent development. But this is still all citation based, and people cite things for different reasons, not only to reflect that they were intellectually inspired by this or that. So let's turn to a different line of evidence that came from sort of my dissertation stuff. This was looking at trying to predict patenting in different domains. So this first one, there's like 450 different broad patent classifications. And this paper tried to predict how many patents are going to come out in a given year in a particular class as a function of kind of measures of the knowledge contained in that class. And we sort of divided it up into two sections. How many total patents have there ever been in this class? And then what's a measure of the combinatorial knowledge in that class? So, this is one slide on a whole paper, so you're not going to get the details. But basically on the left, we've kind of got a bad field where we've learned how to combine ABC, those three classes, many times. And so it's going to be harder for us to come up with anything new that builds on that knowledge. But on the right, we've got the same number of patents, but they've done a bunch of different things. And you can see ABC, BDE, CEF. So we know how to combine B and D. We know how to combine A and B. Could we do ABD? Maybe that's not a big leap. And that's basically what this paper shows, is that guys on the right, you know, when there's a jump in that kind of knowledge, there's a jump in the number of patents that come down the road. This other paper is exactly the same kind of thing, but looking at a much more micro level. So instead of looking at these broad classes of technology, what we're now going to do is say, if we have all these components, say these are 5 components that are taken from actual patent classification codes, we actually know every possible combination that can be pulled out of those. There's 5 pieces, 27 possible ways to combine them if you exclude the ones where it's just one single classification. And so once all 5 of these has been they're out there, they've been assigned to some patent, we can look year by year, what's the probability we see a patent assigned to 2 of them, 3 of them, and so on. And that's what this paper I looked at. And basically, as an example, after we see a patent that combines, say, these 4 guys, we're more likely to see a patent next year that combines some fraction of them, or 2 of them plus the 3rd guy. We're less likely to see more patents that have that exact same 4 elements. So, and also on the bottom side, these effects kind of have diminishing marginal returns. So the first patent like this is valuable, the 100th is not so valuable. Lastly, there's this brand new paper that tries to take this stuff to total factor productivity data. And they have 2 series of data. One is aggregate US data on total factor productivity, and they look at the number of unusual combinations in the patent system. And they show that that's correlated with an increase in TFP 5 years down the road. They also have like 35 sectors, and they try to do a sector by sector test. It's well correlated for 5 of the subsectors, but null results for the other ones. So I think that's the kind of result that normally I'm like a little worried about. Like maybe we're just fishing for statistically significant results. But on the other hand, we've got all this other literature that kind of is suggested that combinations are creating new possibilities. And so I think this is a good example of a paper that is nice in a suite of other papers, but maybe we wouldn't be definitive on its own. So, we've got 4 different ways of trying to document this fact. Patents that bring together unusual ideas are more highly cited, more disruptive. They have more patents that are resemble them, that come on down the road after this happens. And we also seem to see them precede total factor productivity growth, a common measure of technological progress. So why should we care? I think that this is my last slide, so I think I'm good on time here. Sustaining innovation seems like it's going to require finding bridges between disparate ideas to form these new platforms for subsequent elaboration and so on. And there's some evidence that this might be getting harder. Like innovation it seems to take more effort to get an incremental increase in R&D. And one reason that could be is because we're not creating these new combinations as much, because those kind of reset the clock and give us a new highly productive field to work on. And so a policy implication is how can we engineer the collision of ideas that don't know about each other yet? And there's tons of work that thinks about this. Like there's the work on cities and how they are a hotspot for people to encounter ideas they wouldn't normally encounter. Physical offices as a place for people to encounter people they don't normally work with. There's some literature on how outsiders, when they come into a new field, they actually literally do more unusual combinations than the insiders. And then, the internet, as I use Twitter I'm a pretty big Twitter user, and I get way more exposure to weird ideas from Twitter than probably any other single source of information. So anyway, thanks for that. And yeah, I'm happy to take any questions or whatever.
But we didn't say much about the size of effects. Is this explaining 5% of what's happening or 90%?
Yeah, I think for the citation stuff, I remember pretty well that the size of the effect is like, we're going to double or, we're going to increase the probability that you're a top cited patent by a pretty high percentage, but it's from a really low base. So it's like, 2% of the time a patent is a hit, or actually, to 4% or something like that. So I think that's one, and I don't have off the top of my head, but I think in general, the predictive record is not good enough that people are like making a lot of money on this. So that tells you in itself that there's a lot of unexplained variation. And again, that's what I kind of was alluding to, the promise of these new taxonomies. Maybe we'll get richer predictive ability when we're not just saying, class 1 combustion engines and class 2 neural networks, but like we can actually get the details of what's going on. Yeah.
Should I or yes? So 2 quick comments. I think for the patterns you were mentioning that they're citing other patterns.
Yeah.
More and more in the most recent work, we look at patterns that are citing papers, and actually very good patterns are the ones that are citing science.
Yeah.
If that's the case, could we think of university patent paper pairs as potentially the best patterns out there because you have both? And then a question, another interpretation perhaps of your results is that you're mentioning combination is good. But could it be that what you are also capturing is that there are some technologies that are general purpose technologies like semiconductor, AI, that can have so many different applications that you're going to see a lot of recombinations and combinations when you look at the patent data?
Yeah, I think those are both great points. On the question of citing of academic papers, I think it's interesting, that we haven't seen people sort of apply this lens to that yet, and like combining different fields of academic papers. And on your second thing about, are we just picking up that these are general purpose technologies? That's a really interesting point that you could quite easily tease out a lot of this data, like to see if it's always the same class that's being combined. There are some efforts to look at, to define different classes as how easy they are to talk to other classes and which ones aren't. And I think they tend to find that, like these, there's still a lot of value in finding combinations that are not just another application of cloud computing to something new. Over there.
I think the question, I mean, you started off in the beginning, is probably the most fascinating one, because if we knew how human creation takes place, we can go ahead and automate it. It's so there's a lot of efforts trying to, what is it? Is it taking two similar things and putting them together? You have something great that works. It's not as simple as that. So there's something else happening in the process between combining something remote to generating this. And what is this something, and how do you kind of operate that as a, if we knew that part and that element in there, it would be a way the secret to human creation in a certain way. So there's a fascinating part. And just on the more technical side of things, I think there's a lot of strategic citations going on in patents, which make it interesting to see some of these efforts that are being done to do like text comparisons on publications data and on patent data, because you're being inspired by something you're not going to cite. Because you're citing for a strategic reason, you're trying to kind of, patents are strategic documents, so you do them for a certain purpose, and you write them in a legalistic way, so you're protecting yourselves, you're making, I mean, there's lots of reasons why some of these parts are not as interesting to use, and probably really going into the innovations itself, into the patents themselves. And there's a whole of things going on in that literature that I think be interesting to confront too when you write this up.
Totally. I think that on the first point about there's something more than just combination going on, that's 100% true, because otherwise we could really easily innovate by like algorithm, just these two things have never been combined, so go combine them. But there's this old quip, like I can't remember who said it, some famous economist, that like most combinations are like chicken ice cream, they're like not good. And Lee Fleming has a paper that sort of argues that science is one map to help you find the useful combinations. And maybe that's a good complement to your argument about, to Mercedes' argument about papers or patents that cite science maybe are going to be able to find these good combinations easier. My own work, it was kind of like once you make the combination, you've kind of shown it can happen, and then that predicts further people doing similar stuff. But how you find that initial thing is maybe also an answer to Dr. Farmer's question about how can you really predict which ones will be a hit, and maybe because tons of the weird combinations are busts, that's actually why they're not more predictive. And then lastly, on citations, I'm sorry, that I totally agree that they're strategic, weird measures of knowledge transfer, and they've gotten a lot worse since like the year 2000. Like there's papers that sort of show the quality of citations and how much they confer, or like how much they convey is on the sharp decline. So it's good to use more methods than just citation.
Okay, so what's the success rate on new combinations? So if we were to just calculate the flow of new combinations, if you're just mechanically looking in the data for new combinations, and then we define success as people continue on with that combination, right? What would be the success rate? Would it be like a skewed Pareto type success rate, like what we see with venture capital success?
So I don't know about big success, but in my work that I did for my dissertation, there were about like 11,000 elements that could be combined. That was using sort of one level of the US patent classification system. And over the whole history of the United States, only like 2% of the possible combinations among those 11,000 had ever been made. So I think that, it's really rare.
Amongst those 2%, which ones were the ones that really took off, right?
Yeah,
so the combinatorial space is massive, but
Yep.
then there's the realized space, and then there's the subset which is successful.
Right. And I don't know off the top of my
Okay,
head, but I could
cool.
figure it out if yeah.
So I think that was the last question we had time for. So let's thank Matt. And
Thanks.
go to the next. And next, we're going to have Hyejin Youn, who's joining us from Northwestern University and Santa Fe Institute.
Thanks for coming, and thanks for inviting me. This is very interesting workshop. Since COVID especially. So let me wait until my slides is up. Oh, I just used my. Oh, there you are. So I would like to discuss a little bit kind of one step back, and I want to situate myself and originate myself where I am and my model is in the context of everyone is talking about. In between, I may have to excuse myself that I got a COVID 2 months ago, but I still have some throat kind of not coming back yet. So I may have to a little bit, but let's excuse myself. So let me start with this very fundamental question. I study innovation a bit, not all of my work is innovation, but still perhaps half of that. And then I want to make a model. Then I just realized it's just fundamental question. Is it really possible to make a model of innovation? Now, then I step one step back and asking myself, what does a model usually do? And then the two questions, two answers are there here. Explanation, explanatory power, and understanding and prediction. So which one you want to choose more and weight more, determine what kind of model you want to make. So explanation is something like this. I like this, talk about it because it's Stephen Hawking's model-dependent realism. So Stephen Hawking wants to say that we understand the world through our input, through the input of our sense organs, and then build a model to interpret what's going on. So model helps us to understand what's going on, in fact. Now, but it's not the end of the purpose of the model, prediction. Of course, they go hand in hand, but as you can see, there are some two extreme cases. We have to actually sometimes we have to make choices. So understanding, we can be extremely to build a model to understand the things, less to do with the prediction, Or we can just make a machine learning algorithm or AI to make a good prediction, but we don't understand what's going on inside. And I think like toy models are great elements that may not give the forecasting well, but still like allow us to understand what's going on with a few tricks. And AI is on the other extreme, and the Youn has like show the great thing about the ABM, the agent-based model that actually goes really, hold the hands together. So with that, then I realized, okay, so I want to make a model, like it may be possible to make a model of innovation to understand what's going on, maybe not give a prediction, or maybe just give a prediction, but not understanding well. In that case, now the one other question I'd like to ask myself and also the audience is that, are technology innovation predictable? How many people think it's predictable? Innovation is predictable. And how many people think innovation is not predictable? A little bit, yes. This is okay. Like my PhD is in physics, and then I moved to social science at the moment. So I'm teaching at the business school. Then what I learned, what I had to learn over the time is that a lot of a social science problem is like has an ultimate answer that has a little bit of both. So whenever I just say a little bit of both, depends on the situation, depends on the condition. Yes, that they will answer every question in the social science. Anyway, so which is very hard for me to survive. So on one hand, yes, it's an innovation by definition is not predictable, because it's an innovation is by definition is uncharted territory. It's a journey of exploration into a strange land. But on the other hand, there are so many evidences innovation have been predictable. So let me just see the few evidences, I name a few, just cherry picks. The recent article last year, which made a huge controversies, is this paper trying to make a prediction of who's a successful research. So that was like that provoked a lot of good scientists. so here is a machine learning model to make a prediction of who is going to make a huge impact. The second paper I really like, it's done by Luciano the Petronero. They use this skipgram model, that the word2vec that was used by Dan Rackmore, but instead of using it to apply to the corpus, the language text, they actually apply this to the combinatorial process and to make a prediction of which combination is going to be combined in 5 years down the road. And they made a really good prediction. Third, now it's not innovation, but it's an evolution. Even the evolution can be predicted. So a lot of things that are predictable, it's kind of puzzling me, because it's when it comes to innovation. But then again, if I just look at the different literature, different body of literature and the community, intellectual community, then I realize, yeah, like over the 1,000 years, we have been constantly battling between innovation and urbanization. So it seems to be pretty much predictable in the direction, macro direction. And also, like, if I look at the history, big history, increasing, it seems like technology develops over time to make the energy available to be used more intensively. And also the second is technology creates new things, new tools, so that we can actually combine and use to come up with a new idea. And the third is coordination cost. Like a lot of available ideas, but combination is not free. We often forget combination is not free. Interaction is not free. Any communication costs, and it requires that actually they impose a certain structure in the combinatorial structure. So anyway, so in that case, it seems like there is some pathway, the macro pathway I can't really show here, but the drive technology goes through this pathway as if it is its own organism. So in that case, so let me just see whether I can. Oh, yes. So in that case, I can answer to the question is yes. And I try to make try to cut a corner of this. I use a link prediction to make a prediction in the future, and also toy model to see whether I can see some technological space, the simple model, toy model to create the technological space I'm going to share today. And what's the implication? So, okay, so it seems like the innovation is predictable to some extent. In that case, what's the implication of this? We can make money out of it. That's one thing. Yes. Second is implication. Social science, so it's all about implication. So the implication is following. The technology space is a structure change is actually its own object, like own organism. So it doesn't say something about like how great the people have been, I don't know, developing, and it's not about the people. It's more about technology itself, the evolving over time. So it seems like machine. They become machine themselves to make their own way. So that's what I'm going to talk about. The second is because there is no individuals in this discussion, is a prediction is just machine learning algorithm without taking into account any like people features. It seems like the people are just individual efforts is less important. It seems very innovation is a collective behavior. So we want to understand that the large scale the structure rather than individual property. I'm going to talk about this a little bit more here. So the expectation of this would be the multiple simultaneous independent inventors enjoying the ride. So whatever the machine is going, and you want to just jump on and then to move the ride. I mean, it seems like that to me. In that case, if it happened to be the 2 people or 3 people on this machine and enjoy the ride, we may see multiple people who came up with the same idea. And that's one thing I've been trying to do that. So like the examples are, examples are there. The patent on telephone, you have a Bell, Gray, Minucci came up with the exactly same idea, exactly same time simultaneously and independently. Famous example is Darwin and Wallace. They came up with a more or less the same idea of evolutionary theory. Calculus, battles between Newton and Leibniz. It seems to be not the single case. It seems to be the case recurring many times. So one of the things I try to see is that whether this is the case in the real, in the recent kind of modern technological history or modern era, that we just look at how many people who came up with the exactly same idea. That's what I'm doing. And it's not the new thing. It's not a new evidence that we have known that. And some people like Thomas Kuhn, for example, once stated that the time must be ripe, so that we came up with the exactly same idea. People have to somehow here in the group of people here, and we listen, we talk, and somehow there is some ideas bubbling up, and the ideas is up in the air. And if you are lucky enough, then pick up the idea and make a name out of it. So here is the small conclusion, the little conclusion. Innovation is a collective behavior of a messy network. So I would like to construct a network from some micro strategic decisions of individuals. So where to start? This is a starting point, exploration, exploitation. This is Jim March and many people. It's a classic beginning. And I'm going to show how fundamental this phenomenon is in real life, not only just applicable in innovation, but also in the many decision makings you are doing, like going to the restaurant, for example. It's a choice between exploration and exploitation. Like, do you want to go to the restaurant you already like, or do you want to go to something new, which has a risk? And there is always a good point between the best strategies in something between two. And I find I also find that this ratio between the exploitation and exploration seems to be invariant over the 200 years in US patent. So, so in that case, how do we quantify exploration and exploitation? So novelty, like one example is novelty. How we quantify novelty? Is it just any new combination is novel? Or there is some degree of novelty extent to which the new combination is novel or not. So I make a novel, quantity, novelty quantity or conventionality by 5 minutes, by looking at the difference between the expectation and observation. So let me just go here, novelty. Let me see whether, no, it's not. Oh, yes. The novelty here, the differences between observation and the expectation. Expectation comes from your null model. So from your null model, whatever null model you have in your mind, you have some expectation how many combinations will happen from the learning you had done. It's a very agnostic here. And the observation is what really happened. And the more distinct description between two have the higher novelty if it's minus is, and it also this number actually gives a really great idea that how to quantify the conventionality, emergence of conventionality. So if you find that some combination happens more than excessively many times, like more than you expected in random chance, that means it becomes conventional. Somehow these two ideas combined so many times for some reasons. And maybe it's a reason, it's a functionalism. They are fitting together very well, or something like the people like it and somehow, and we made a consensus and the feedback loop, get richer effects comes into play and normalized by this standard. Oh, there you go. Deviation. Oh, yes. So once I quantify this novelty and conventionality, now I ask, okay, how does novelty actually do for your impact of the patent or the scientific paper? We find that something interesting. One, you can see that the green one is a broad profile of the novelty measure. So if you look at the patent or your paper, it actually applies to your paper as well, the scientific paper and patent as well. If you look at that, then you have a multiple combinations. If you have a A, B, C ideas, then you have a three different three pairs. And we look at the novelty profile of the three pairs, Z-score I just showed. And if every combination is so novel, which is the red here, not going to be great. And if everything is very conventional, it's actually better than too novel. And then if something is broad, that the combination is something really novel, and but also conventional, with some conventionality, then that's the sweet spot. That's like something like the mantra from the beginning of my this research. Brian Lucy has done a really great job, my senior faculty in my department. And ever since this, and I try to make sure that my paper has some little bit of novelty, not too crazy, but but make sure that I have some element of a conventional intellectual group, intellectual community. So I try to make like conventionality and always make sure what's the element of conventionality in my paper. So with that, so what's the reason? What's the reason that we have this sweet spot, like between the collinear relationship? The one reason is that infrastructure, no technology stands alone. If something is new, how can you implement this technology in this physical space or the existing infrastructure? So the famous example is the autonomous vehicle. If we didn't have enough to support the data processing, it wouldn't have been, successful. So there is some time, novelty is also dependent on the function of time. So it's not, it could have been novel in the past, but it's not novel in the present. So you always have to take into account what's going on here, but you also take into account this factor of this conventionality as well. Second example is that it's not about physical space, physical infrastructure, but also our interpretation, our understanding of the technology. So if the idea is just too novel, how can I even understand, to evaluate and like? We don't like, in fact, it is true that we don't like a new thing. We often think novelty is great, but if something is too new, we hate it. That's why we have to actually meet each other often, and then we kind of like it. The one example I just brought up is the wine. The first time I tasted wine, I hated it. How many people actually like the wine at first time you taste? It's what is called acquired taste. You get to like this taste. This is a stinky tofu. This is ethnic food, which people once first you come across, you hate it. But over the time, you get to like it, and sometimes you become a fan of it. This is actually the curvilinear here is a research output of the grant, the proposal, evaluation score of the grant proposal. X-axis is a novelty score, and the Y-axis is evaluation score. Just keep in mind that whenever you write a grant proposal, not to be too wacky, because it's going to be the lower score than the the too boring proposal. So it seems like we don't you don't really want to be too innovative in that case. Okay, so 1 minute. So 1 minute, I will just give you some idea of what's the model I have. So I just take into account this model of exploitation and exploration. Every decision is made between the exploitation and exploration. So I start with I make a growing network. There's a network that grows from the small handful of nodes to the thousands and the 10,000 or the million nodes. And I from this strategic micro strategies. So knowledge is structured. These nodes are ideas, and ideas are combined when they from my individual point of view. So I have a domain knowledge C sub Z. C sub 0 is not, and then I can't really explore longer. So occasionally I have a discovery rate that T to the minus delta, and then I explore from this knowledge space structured proportional to what is well being paid. So thicker link means it has been conventional. It has been combined so often, so I just have a more tendency to combine those. And I can go a little bit like a longer distance, but the chances that I make a connection to the long distance idea is smaller and smaller and smaller. It's exponentially decreasing in fact. And then I combine. And if I just make the growth of the network, and it looks like this. But how do I validate? So here is some statistics like micro statistics, network statistics, a clustering coefficient and strength growth and all kind of a clustering coefficient and degree distribution and all. Then I just match with the academic papers and pattern data. And I can just skip because I think Matt has done really great job on this, explaining this, how combination is made. And then these are the two bottom rows are empirical data. The first row is the counterfactual world with this simple model, and they looked very much similar to each other. So, okay, with that, I can make a counterfactual world with a different exponents like parameters of the exploration rate and exploitation rate. And all this the heat map, every point is a pair of the variables, the parameters, a pair of parameters. And I can situate our real world, our world we live in, here, there. Seems like we are going to the reach of the modularity. So by the way, the color represents the modularity score. Why modularity is important? Because it's related to the recursive technological recursiveness. If something is combined so often and group of technology put together so often, it becomes a module itself, and it becomes act like it's an owned unit. So now it's going to the next level of the hierarchical level of the technology units. And also you explained a little bit of the discontinuity of the phase transition of the technology advances. So the technology doesn't advance continuously, but somehow like discontinuity, and maybe explained by this modularity score. So let me just, and it's like going back to this Thomas Kuhn and all, and we can discuss during the coffee break. So conclusion, and thank you.
We're going to have time for one question, but Hyejin is around, so anyone who has questions, and I know I have many, we can catch up with her over the coffee later, and we have someone at the end.
Hi, firstly, great presentation. I loved your graphs. So, and I actually, what you said about technology innovation is very true. I thought of Blu-ray versus DVD battles and the VHS versus Betamax back in the day. Anyway, so what I wanted to ask you, focus a lot on microdata decisions, but I think there's a role perhaps at the state or some other sort of, large, I think you use the word environment that could play in sort of driving these micro decisions. So I would love to hear what you would think about that and sort of how the different roles of these two things, micro versus macro.
That's an excellent question. So my philosophy is to make a model as simple as possible, not to take into account as long as it's absolutely necessary. So with this like really simple model, with not taking into account any kind of heterogeneity of the environment and all, it can produce the modularity, but this modularity structure doesn't actually mean the reflection of real structure. So I can't really say that. So maybe that is the part where I can introduce this environment and particular pathway, historical pathway or our society has taken, and whether that is reproduce this, that's a good question. Thank you.
Okay, so we're going to move to Mirko, but let's thank Hyejin for an excellent presentation.
Thanks. Shall I start one?
Yes.
Okay, so this is sort of an abridged presentation of some work that I've got with Vasco Carvalho and Nicholas Coulin. You can get the full paper off my website. So Exploration, Exploitation, US Technological Change. Okay, so in the economics of innovation, sort of following Grillicki's summaries, we've got three ways that we tend to measure kind of innovation or technological, well, more like technological change broadly. So firstly, there's outputs. Okay, so patents, scientific papers, often we modify those with citation counts to measure the quality of the output. Secondly, we've got inputs, right? So we measure technological change or innovation in terms of inputs like, you know, what we're putting in, like R&D spending, employment of scientists and engineers, investment in technological capital, and more recently, intangible capital. And then finally, the third main way that we have for measuring innovation or technological change is total factor productivity, right? So TFP estimated from production function methods. Now, we know that these methods face challenges when it comes to understanding qualitative changes in technology and rates of what we think about as progress, right? So it's been said a couple of times today, you know, we've got this observation that we've made that there's lots of innovation, or there's lots of technological products, and there's lots of inputs that we're using, but not enough growth associated with that. And we also know that there's ongoing changes in the heterogeneity of the economy. There's lots of inventions being created. There's new variety being introduced all the time. And then another challenge in terms of trying to measure innovation technological process is kind of linking technological change to the process of innovation. As we've discussed, we know that innovation is all about trial and error and experimentation, and this is complemented, this trial and error and experimentation is complemented by periods of consolidation where we double down on successful experiments. Further to this, in general, we know that there's qualitative change going on in what is studied, right? We know that different sorts of heterogeneous ideas enter, rise, and fall. There's waves of development. There's waves in the development of ideas. So this is where we start to try and use text to see how we can kind of move forward. So text data offers this chance to try and capture what was previously thought of as qualitative change and how it relates to progress. So what we're going to put forward here is an innovation measure, or technological change measure derived from the probabilistic text information in patent documents. We'll see that this can be a general method for analyzing structural change in any text setting. In short, it's going to collapse down to looking at how the probability distribution of words changes in a given set of scientific documents. Okay, we're going to illustrate this with the case of IBM using US Patents Office data. IBM is a great case because it nests the development of ICT over the 20th century. Hence, we get to see ICT developer evolve. Okay, and the basic intuition behind what we're going to think of as an exploration measure is we're going to ask how differing is IBM's patenting this year compared to previous patenting by IBM, right? This will be measured in terms of informational bits. Specifically, what we're going to be working with here is changes in the probability distribution topics, right? So how are the topics that IBM are working on different from year to year? Okay, we're going to say a bit glibly that periods where there's lots of change in the probability distribution of words or topics, we're going to see those as phases of exploration, while steady periods we're going to call exploitation. But I'm fully open to, so just, Hyejin offered a much more kind of rigorous approach to the exploration and exploitation sort of modeling issue. But crucially, what we're offering here is, this is going to mean that lots of patenting just because IBM has produced a lot of patents in a given year doesn't mean that it's moved forward in terms of novelty, right? So more patenting in quantity terms doesn't necessarily mean lots of innovation and novelty. Okay, so we're going to start simply. We're just going to look at word frequency within IBM patents by decade. Specifically, we're going to look at the fastest growing words in the IBM corpus for that decade. And this is going to give us a proxy for the new sub-technologies that emerged within ICT in a given decade. In this case, what we're going to see is we can clearly eyeball the evolution of ICT. It's showing up in the word frequencies, right? So here what we've got is per decade, we've looked at the words in IBM's corpus that have grown the most quickly, right? So the fastest growing words in IBM's corpus. So if you look over in the 1930s, and you can really see, tangibly see the evolution of ICT. If you look at the 1930s, you see kind of pre-analog technology, you know, words like mean, feed, select, gear, sheet, you know, character. Going into the 1940s, you can see the development of analog technology, card, machine, tape, electron, number, you know, column, you know, performance, etc. Finally, in the 1950s, we start to see digital technology, keywords to do with digital technology emerge, circuit, magnet, data, signal, input, and so on. Finally, down the bottom. And then, you know, we can further see this. IBM's such a great case study. Digital continues in the 1960s. We sort of see microcomputers develop in the 70s and 80s with words like silicon, layer, data system, document, access, user, circuit. Finally, in the 1990s, you start to see the beginnings of internet technology, user layer, system, content, request method as poetry, right? So that's just like looking at how the kind of the word frequency, the distribution of words is changing just in simple unigram terms for IBM. So the next, you know, so that's just giving you an idea of like when we cut up the data, we can clearly see that there's action in the word frequencies, right? So the next step here that we take then is dimension reduction. So moving beyond word frequency, we want to group words into topics and look at how topic shares are changing across time. The point of this is that topics are a better summary of the structure of the data than just using simple words, simple unigrams. Not to get technical, it's not the time for technicalities. I think a lot of people know this stuff. We're using standard LDA topic models. If you're not into that stuff, just think of this simply as word clusters, specifically describing documents as mixtures of word clusters. To illustrate what we're doing, so we're just moving from unigrams, simple one-word phrases, to topics like these clusters of words. I'm just going to show you what, if you run a 10-topic model, a fairly low-dimensional 10-topic model, and then look at how the topic shares change over time for IBM, what do you get? Okay. So this is giving you 10 topics from 0 to 9, and it's showing you how those shares change, depicted in terms of a heat map. And what we've tried to depict here is that there's a fundamental change in the topic structure around the mid-1950s, right, where a bunch of topics sort of tend to become obsolete or move out of existence, and then a whole bunch of new topics tend to come in, right? And that's what you're getting out of a 10-topic structure, analyzing the topic shares in terms of, how IBM's are kind of topic shares are different from year to year. And then the next step that we do, or the final step, is to build some kind of summary measure. So can we summarize this in terms of one number? Yes. Okay. So to do this, we first run a model for 100 topics across all of IBM's patents as a flat cross section, and the number of topics doesn't really matter. The banner is robust to that. Then we calculate a Kuhlbach-Leibler divergence measure that can be interpreted as Bayesian surprise or relative entropy based on evolving topic shares. So here we're drawing on work by these two teams, kind of involving Simon Dio at Carnegie Mellon. Again, it's not the time for technicalities. The way to think of this is that you run, let's say, a 50-topic model. You've got topic shares. You've got 50 elements in the vector. We're looking at the difference between those two probability distributions. We're just calculating the log difference element by element and then weighting by the prior, all right, and then summing it up. So it's a fairly simple, don't be confused by the notion it's relative entropy. John von Neumann, no less, said no one knows what entropy means. So, okay, and all this is just quantifying is how different is the topic share distribution this year compared to the topic share distribution last year or some average of previous years, okay? And when we do this and calculate this chaos divergence measure, we can indeed see that there was a major shift in the 1950s, right? So this is our exploration measure. This is showing where sort of kind of IBM moved into a wildly different area of its knowledge space, right? And that this was the fundamental structural break, which is essentially the move from analog to digital and computing. And then this is just giving you the accumulation of that exploration measure, just to show you how kind of that was a level shift in exploration. So IBM moves up, has this massive phase of exploration and moving from analog to digital. And then there's this smooth period of less marked exploration that we're sort of a bit glibly characterizing as exploitation. Okay, so that's giving the IBM case study. As I said, that's like a great case study because it nests the development of ICT over the 20th century. The next thing we do is extend this by calculating the exploration measure across US firms. We're using the well-known CompuStat CRISP data, allowing us to look at exploration over the life cycle of long-lived firms with big patent portfolios. This indicates that firm exploration slows with age, and that this slowdown is more acute than similar declines in overall firm growth, right? So this is what you get when you calculate cumulative exploration across this panel of big, long-lived firms, right? So we're seeing this sort of classic S-shaped pattern that we tend to see in lots of innovation data, okay? Where you're exploring a lot, okay? You're exploring a lot, so you slow down a bit, and then you slow down a lot as it tapers. Right, so we're seeing that sort of shape amongst long-lived firms. And then if we sort of just throw this through a regression, right? So what we're seeing here is that the blue line reflects the gradient, 5 minutes, the gradient for the cumulative exploration. So that's showing how exploration slows down with age. And the red line is showing you how firm growth slows down with age, okay? And the interesting thing here is that firms are exploring less as they age. So this would point to the classic Schumpeterian debates of the bureaucratization of innovation. So I think Schumpeter jumped between thinking big firms are great for innovation versus thinking big firms are bad for innovation, right? And this is sort of suggesting bigness is correlated with age, so age might come into it, right? So it's giving us these interesting relationships across firms, okay, in terms of the life cycle of firms. Finally, the really big test here, and it's where I think probably, we've got a niche adding to Hyejin's work, right, is the big test is firm growth. Is this exploration measure that we've calculated correlated with firm sales growth, right? So people working in my research tradition, that's what we think matters, right? Does it explain something economic, something solid and economic? Amazingly, yes, right? We run a battery within groups and different specifications with trends and importantly controls for the quantity of patenting. And there's a consistent pattern within firm correlation. That is, when a firm's exploration, when a firm has a burst of exploration, it has a burst of sales growth on a within firm basis. And I think this is remarkable insofar that, think about what we've got with this exploration measure. It's essentially a measure, it's picking up probabilistic text information. It's stuff that's functionally invisible, right? It's just picking up changes in the word distribution, right? And we're controlling at the same time for the quantity of patenting. So we're already throwing in how many patents they're spitting out, right? And then we're looking at deriving this thing about the qualitative nature of the text. In the paper, we've got more information about the regressions, but it's a kind of robust result with a kind of clear lag structure. It's hard to quantify. It's hard to give you a magnitude because this is kind of quantified in terms of bits, but essentially like a 1 standard deviation shift in exploration is equivalent to about 1.5% sales growth, right? But it's something you really need to think about in terms of big bursts of exploration and how it sort of works within the overall life cycle of your firm. Okay, so conclusion, right? So I think what I've been trying to convey here is that, text-based measures of kind of innovation or kind of more precisely here, novelty exploration can meaningfully move us forward with respect to the measurement of innovation and technological process, right? So in addition to inputs, outputs, and residuals, now we've got this option of looking at qualitative change using text. right? But this isn't full evolution yet, okay? One step would be to formally link this kind of measure to how diversity is changing. So for example, a surge in exploration for a given firm or any given unit in the economy doesn't necessarily mean increase in diversity, right? So, you know, when IBM switched to digital and went all out to digital, it may have kind of reduced the overall heterogeneity of its innovation activities. And then finally, there's, you know, this, as I said, it's a measure that we've borrowed from kind of Simon Dio's teams that they've used in different contexts. And there's lots of scope to use this, you know, fairly straightforward KL type measure and interpreting it in different ways. So the most obvious non-economic domain for this measure is the media. So, you know, with this kind of measure, we could finally measure news cycles and what we think of as information acceleration, right? So you could measure things like when COVID comes along, how that completely changes the composition of news and crowds out other topics and leads to topic change. Similarly, when the Russia-Ukraine war comes along, how that changed the structure of news, right? We can even think about notions of how fast is the news changing? Are we seeing kind of acceleration in information overall in society? Okay, I'll leave it at that. Yeah.
Fascinating. So as I showed your figure about IBM, you know, #1 patenting firm in the US, like a real screen. I wanted to see how this is happening. There is a lot of work written about the role of the CEOs, the CTOs. Very often the CTOs are top inventors themselves. So I would love to see in your graph about the evolution of IBM over decades. Who are the CEOs and the people that are driving this transformation? So I know it's separate, and the how this happened. And often the how is going to be leadership and the people in those. So I would love to see more of that. And there is a very nice paper written by a Harvard Business School professor about that evolution of the CEOs and how that is affecting the transformation of
just
IBM.
quickly, the easy way to do that is we just put in CEO and CTO fixed effects, right? Bertrand and Shaw type stuff. That's a great idea. Yeah, there's one.
Thank you. I think you showed there that an increase in innovation is associated with an increase in sales growth.
Yeah.
Have you done work to show the opposite effect, the decline in innovation leads to an increase in failure or decline in sales growth?
No, what we've got, like what I missed out is we have this measure of successful exploration, which is saying, okay, you do something different and then you stick to it. Right. And that's what gives you the biggest bang. Right. So that's passing out really successful innovation. I guess we could compute the inverse of like that and say like really unsuccessful experiments. So it's a great idea. We can actually try and do that and see if it's asymmetric. Right. Because that will point to the riskiness of innovation. Two great ideas already. Thanks, guys.
When you're doing your analysis of all the firms and you have 100 different clusters, are these like within firm clusters or is this like for the whole sample? Because I could imagine, you know, there's a difference between me moving into a sector pioneered by somebody else and kind of being a copycat versus exploration, like, you know,
so it's a great clarifying question. So it's all within firms. So you run the topic model on just IBM's patents. So you need the big firms to have big portfolios. We've tried that stuff of kind of moving across firms. That's where it gets messier and harder to tease out. So it's on a within firm basis, and that's why we lean on the within firm correlation of sales. It gives us that, right? But great, useful question.
Thank you. I think it's really interesting. I just want to follow up this question. So because what you show is on average, firms' innovativeness or innovation leads to better performance. But what is the role of the market structure in competition? Because the competition level or competitiveness of individual compared to within the narrowly defined industry is not going to have the linear kind of relationship with performance. So in some cases, the firms would rather not to innovate to protect its rent. So very much how much you benefit from your own innovation really depending on what everybody else is doing.
Yeah. The classic thing to look at here would be an inverted U, right? With competition innovation. And so exploration competition and exploration. I think, and so competition helps exploration up to a certain point, and then it kills it, and you have an inverted U, and that's like the classic, Aghion, Blundell, Bloom, Griffiths paper. I think we started to look at that. It doesn't pop out. It doesn't pop out the data, but that is an obvious. That's an obvious route we might develop on that. Right? Is industry relationships, but it's a great observation.
Thanks, Mirko. That this is great. I guess I was thinking that in some ways, I mean, you're interpreting this change as exploration, but we could also call it volatility.
Yeah.
And I guess I was just going to say that it would be quite nice if you complemented your measure of exploration with a look at the actual patterns that are generated when exploration happens, and whether those patterns are more influential.
Great idea, yeah.
Because they are more cited or they are more novel, using some of the other metrics we have been discussing in this session and before, just to confirm that we are looking at exploration and not just like some sort of like process of volatility in what firms do, perhaps driven by.
I guess it would be that the patterns in the surge exploration years, they should turn up as more highly cited influential patents. You're right. Yeah.
If it's successful exploration.
Yeah, if it's successful, yeah.
And I think that was the alarm saying that we're out of time for questions. So thanks so much, Mirko.
Okay, thanks, guys.